So now that we've gone through some of the basics about what are the properties of sound, we're going to be covering the functional anatomy of the auditory system. So the ear collects sound waves from the surrounding air, and it converts this mechanical sound wave energy into electrochemical neural energy. And then this is then routed through the brainstem to the auditory cortex. So first, let's go through some of this basic functional anatomy, okay? So here's your ear, okay? This is your pinna, this is the outside, and this is what enables the better collection of the sound information. Your ears are uniquely built to, if sound hits it, to redirect it so that it comes into the middle of your inner ear. The sound wave comes in, and here you have your middle ear, which is comprised of your ossicles and your semicircular canal here into your, and then here you have your inner ear. So the pinna catches the sound waves and deflects them into the ear canal, and then the waves are amplified and directed to the eardrum, causing them to vibrate. So here's your eardrum right here. So again, this mechanical energy comes in here and it causes the vibration of your eardrum. As this vibrates, it in turn vibrates the ossicles, okay? So when these vibrate, the ossicles, again, they continue to amplify the sound, so they increase its detectability, what is meant by amplify. They make it basically get a little bit louder inside your ear so that it can be detected better. And the oval window then transmits these vibrations into the cochlea, which is where your receptors are. So here, you can see this vibration of the oval window. The vibration of the oval window sends waves through this cochlear fluid right here. So this is basically like waves on water, waves in a bathtub. If you've ever made Jell-O and it hasn't completely solidified and you touch it, then it kind of vibrates, especially when it's like little pieces of Jell-O. That mechanical sort of pressure that causes vibration, that's basically what happens in your oval window. These vibrate, then it causes the fluid in here to vibrate, okay? Or the fluid in here to change. Then when this sort of waves are sent out through this fluid, okay, you have these hair cells that have their little tips up here in this fluid. When the waves here occur, okay, they're sort of like, this is basically, they move from the vibration, then you have your receptor cells, which basically have their little tips right up here inside this fluid. And then these outer hair cells that are embedded in this membrane, they bend. And when they bend, this generates neural activity, which would convert it into the electrical chemical neuroenergy. And if you want to think about how these cilia function, if you've ever seen how kelp sort of waves along with the tide, as the tide goes in and out, that's kind of what could happen with these cilia, that they are up here, and then as this moves, then the cilia move, and as the cilia move, they bend, and this generates a action potential. And in this way, it is converted to electrical chemical neuroenergy that is routed through the brainstem to the auditory cortex. So reviewing the structures of the ear a little bit more, okay, what is included in the outer ear is the pinna and the external ear canal. So the pinna is a funnel-like structure designed to catch sound waves in the surrounding environment and deflect them into the ear canal. And the external ear canal amplifies those sound waves somewhat and directs them to the eardrum, which vibrates in accordance with the frequency of the sound wave. Okay, so this is important. So the eardrum vibrates in accordance with the frequency of the sound wave. And again, this is right here. So if you hear something at a high pitch, then your eardrum, as this wave is coming in there, is vibrating in accordance with that pitch. And these are the two parts here, the pinna and the external ear canal, that make up the structure of the outer ear. Next, after the outer ear, is the middle ear. Okay, so the structure of the middle ear, this comprises the ossicles, the air-filled chamber that comprises the ossicles. So the ossicles, these are bones in the middle ear They are specifically the hammer, anvil, and stirrup. And they were named these based upon how they look. So the ossicles, the hammer, anvil, and stirrup, connect the eardrum to the oval window of the cochlea. And the cochlea is located in the inner ear. So here are the ossicles. And again, sort of looks like a hammer right here, looks like a hammer, an anvil, and here, this clearly looks like a little stirrup. So again, the waves are amplified and directed to the eardrum, causing it to vibrate, which in turn vibrates the ossicles, and the ossicles amplify and convey vibrations to this oval window. Next, we have the inner ear. So the inner ear comprises the cochlea. And the cochlea is sort of this snail-like structure on which you have this whole section that where all these hair cells sit. And the vibration of the oval window sends waves through the cochlear fluid. And as this fluid sends these waves through, these waves then correspond with the frequency of how the eardrum was vibrated. So the waves correspond with the frequency of the sound wave. And these waves in the cochlear fluid cause the basilar and tectoral membranes to bend, in which these hair cells are embedded. And so when the tectoral membrane bends, then the hair cells bend, and it results in an action potential within the hair cell receptors. So now we have this overall sensory pattern. The same thing that we talked about for vision, we're going to be applying it for the auditory information as well. So we have our receptors, which are our hair cells, okay? So these are our receptors. These hair cells, these are sensory neurons in the cochlea, tipped by cilia. Cilia is just little hair. When stimulated by waves in the cochlear fluid, our hair cells generate graded potentials in inner hair cells, which act as the auditory receptor cells. And the tectoral membrane is the membrane that's overlaying the hair cells. It's what the hair cells sit in, and it's what vibrates. And when it moves, then it moves the cilia, and that causes action potentials in hair cells. So again, here's a close-up example. And here you have your outer hair cells. These are going to move. And when these move, they bend, these cilia bend, and it causes graded potentials, which can result in an action potential in these inner hair cells. So the hair cells are the receptors. The hair cells are the encoders of auditory information. They transduce sound waves into neural activity. This principally takes place in the hair cells. So as I said, when you listen to really loud music, then what can happen? That you can have hearing loss because the sound can be so loud that it damages the hair cells. And if you damage the hair cells, then you damage the receptors, and then you lose the ability to hear particular sounds. And what ends up happening is the louder the music you listen to, then you damage some of the hair cells that are really sensitive to softer sounds. And so then you need to hear things louder to, again, hear even those sort of softer sounds, and which of course over time can result in you sort of yelling at a person so they can hear, because they've listened to music or they've heard really loud sounds, machinery, all sorts of things that have damaged their more sensitive hair cells. So you have about 3,500 inner hair cells. These are your auditory receptors, and you have 12,000 outer hair cells. And what these do is they alter the stiffness of the tectoral membrane. So the movement of the basilar membrane stimulates the hair cells via bending and shearing action, and movement of the cilia on hair cells changes the membrane potential and alters neurotransmitter release. So in the end, what you really want to know is that these inner hair cells and outer hair cells work together to convert the sound waves to electrochemical energy that is then sent to the auditory cortex for future processing. So here's an example of how this works. So here you have your cochlea. This is in your inner ear, and it's a sort of snail-like structure, okay? So what you need to know about how this cochlea works is, again, you have the movement of the basilar membrane in response to sound waves. So this membrane moves, and when this moves, this creates a shearing force that bends the ciliate in contact with and near the overlying tectoral membrane. This bending generates neural activity in the hair cells from which the cilia extend. Okay, so this bending generates neural activity, and it is sent down. It's sent downstream. This is the axons of your cochlear nerve, which would be your auditory nerve, and so this bending sends these downstream. If you have the inner hair cell here, which is going to come in contact with your tectoral membrane ever so slightly. Okay, so you can see that when this has moved up, then it's pushed up against here, and then it's going to change the stiffness of the tectoral membrane, which will then change how it interacts here with this inner hair cell. So basically, you have the wave that comes in here, it pushes these up here, okay? When it pushes up here, then you have this shearing action. This bending generates neural activity because the hair cells are mechanical. So when they get bent, it's going to cause a graded potential. And again, what's a graded potential? A graded potential is an increase in positivity that makes the cell more likely to start an action potential to signal and convey the information that a particular frequency has been sensed. So this displacement here in the basilar membrane, this corresponds with the frequency of the information of the sound wave. So it also corresponds with amplitude. So the louder the sound is, then the more greater displacement you'll have up in here. And then this frequency is going to result in displacement or this sort of waveform that's going to be of a particular size or shape. And what happens here is that this is just a cross section of your cochlea, but you have this hair cells all along in here. And so all along in here are hair cells, and that this basilar membrane is going to move, and it's going to move in line with a certain frequency. And so you have hair cells that detect different frequencies along this curved path that comprises the cochlea. So the movement of cilia towards the tallest cilia depolarizes the cell, causing calcium influx and the release of neurotransmitter, which stimulates cells that form the auditory nerve. So it stimulates an action potential, and the nerve impulse increases. So again, here's movement towards the tallest. Okay, so they've been pushed movement towards the tallest. So this directionality here, in terms of tallest to smallest, is important. They're pushed out this way. Okay. So that stimulates firing. Movement of the cilia towards the shortest cilia, this hyperpolarizes the cell, resulting in less neurotransmitter release. And so this is activity in the auditory neurons decreases. Okay, so more activity bending towards the tallest, less activity bending towards the shortest. In this way, you have these sound waves that are going to come in and continually displace this basilar membrane, which is going to cause these to move against the tectoral membrane, and the way and the direction that they move is then going to result in the firing of an action potential or the not firing of an action potential. Now, I know this is definitely a little complex, so make sure that you read the textbook as well to best support your learning of this material, because it'll be really beneficial to hear it from multiple agents.